Hi, I'm Kaiping. It's a pleasure to present our work on capturing feature-level irregularity in disease progression modeling. This work is in cooperation with NUHS. In this talk, I will first introduce some background information and then review some existing solutions for irregularity. And then I will discuss our problem definition, present our methodology, and finally, I will present our evaluation results as well as some case study results. Okay. To start with, chronic disease is a major cause of illness and death, and patients' conditions are likely to worsen with more severe complications and comorbidities without timely and proper intervention. So to help with this issue, disease progression modeling is proposed. It can employ computational methods to model the progression of a target disease. And with an accurate model, disease progression modeling can facilitate early detection and treatment of chronic disease before the deterioration. And generally, disease progression modeling exploits electronic medical records, EMR data, for analytics. EMR data is time series data that records patients' visits to hospital. Generally, EMR data includes all kinds of medical features, such as diagnosis, lab tests, medications, procedures, and so on. When we employ the disease progression modeling over the EMR data, one major issue is the irregularity issue over the time series data. And there are two levels of irregularity, the visit level and the feature level. The visit level irregularity means that the visits are very irregularly spanned with time, and the time span between consecutive visits is very irregular. And the feature level irregularity means that the same feature appears irregularly in EMR data with time, and the time span between a feature's consecutive occurrences is irregular. Let's look at an example. In this figure, this patient visits hospital 4 times, and his visits are very irregular. The time span are respectively 9 days, 3 months, and 6 months. In the upper part, we can find the visit level irregularity, and in the bottom part, we can find the feature level irregularity. And we note that the feature level irregularity is caused because this patient does not always receive the same set of diagnosis and lab tests at every visit. Now I will review some existing solutions for irregularity in EMR data. Among the existing solutions, one category of method tries to convert the time series data into non-time series data. Such methods enjoy the advantage of simple computation and modeling. However, the performance of such methods might be affected due to the underutilization of time series data. The second category of methods transform the irregular time series data into regular time series data. Some methods may employ the dynamic Bayesian networks for the good causality and interpretability. However, it might be time-consuming to construct a model with the expert's domain knowledge. And some other methods try to use the deep learning models for the better performance in many tasks in the feature learning. But such methods might involve to partition the irregular time series data into time windows, and then, therefore, it might be difficult to capture the feature patterns in the time window. The third category of methods utilize all the EMR data available without any transformation. Such methods may input the EMR data just in chronological order without considering the irregularity challenge. And some methods may utilize the irregular data by concatenating the visits timestamps as a new feature in the input. And some methods may use the time span as the visit level decay term for the analytics. Such methods has the advantage that they can incorporate all the EMR data available. However, they cannot utilize the feature-wise time span information, or they cannot distinguish between different features. So now I will present our problem definition. In our disease progression modeling, we have some known data in the history incorporating all the medical features collected and known. And our objective is to predict the patient's future severity, which is unknown. So then we can define a cut point between the known history and the unknown future. So formally, we are given a set of examples in the form of a triple composed of X, which is all the known medical features in the history, Y, which is the future severity we want to predict, and the delta T, which is the time span between our future Y and the cut point. The objective of our disease progression modeling is to obtain the mapping function phi, which can minimize our defined loss function over all the training samples. So now I will present our methodology. This figure shows the model structure if we utilize the standard gated recurrent unit. In this figure, we feed our known medical features through the input layer, and then we use the GRU layer for computing the temporal behavior inside the data. And then we combine our output from the GRU layer together with our time span information as we discussed before through a combination layer. Finally, we feed our output from the combination layer into the output layer, which can provide us the final prediction result. We define our loss function and use the backpropagation algorithm for updating the model parameters. However, this model cannot capture the feature level irregularity as we discussed before. Therefore, we propose our adapted gated recurrent unit shown in this figure to handle the feature level irregularity. Specifically, we will compute a decay term rho here using the feature level time span information and multiply this decay term to the update gate ZT, which can trade off between the previous hidden state and the temporal hidden state when we're computing the current hidden state. Now I will show our evaluation results. We evaluate our proposed method through two datasets. The first one is a public Alzheimer's disease dataset, and we use the mini-mental state examination test to evaluate the patient's severity indicator. The second dataset is extracted from a chronic kidney disease CKD dataset from National University Hospital. We choose the patients with the stage 3 chronic kidney disease or higher as our cohort, which means our study group, and we denote it as the NUH-CKD dataset. Then we use the lab test glomerular filtration rate as our severity indicator for the patients. And we use the mean squared error and the Pearson correlation coefficient as our evaluation metrics. Here are some statistics for our two datasets with some basic information and the corresponding number of samples in each cut point setting. We compare with some GRU-based methods. The window-based model is to partition the irregular time series data into regular time windows and then aggregate the records within each time window. The visit level model tries to resolve the visit level irregularity by concatenating the time span information between consecutive visits as a new feature. And the visit level time decay model uses the visit level time decay, use the visit level time span information as the decay term for the updating parameters. And we also choose some multitask learning methods for comparison, including the least convex fused group lasso and two formulations of the least non-convex fused group lasso. Okay, so this is our experimental results in the public ADNI dataset. We can find that for the same cut point setting, from the window-based model to our proposed feature level time decay model, the performance is mainly on the ascending trend, which proves that to capture the feature level irregularity can contribute to the performance of disease progression modeling. And we also notice that our proposed feature level time decay method can be more accurate than the multitask learning-based model because we can actually utilize more time series data. And we found that when our cut point becomes larger, the MSE values of our proposed GRU-based models can be decreased because we utilize more time series data. Okay. And here are the experimental results of the NUH-CKD dataset. We found that if we change the cut point setting from W16 to W24, we find the GRU-based models can achieve larger MSE values, which means the performance is degraded. We figure out this may be because the decreasing number of samples during this cut point setting change. And if we further increase the cut point setting from W24 to W32, we find that the GRU-based models' performance is actually improving. This is because through the time changing, we can utilize more time series data in the cut point of W32. So in a nutshell, both the sample length and the sample number will affect the model performance. So now let's look at some case study results. We choose 3 example patients with representative disease progression trajectory for doing the case study. Our objective is to predict the patient's future severity in terms of the GFR value, the lab test value. And please note that the GFR value, the lower, means that the patient's condition is more severe. The green triangles here means that the already known and the known ground truth values which will be fed into our model. And the orange ones means the unknown part, the ground truth part, which can be used for evaluating our prediction result. And the blue curve here means our prediction result from our feature level time decay model. So for this first patient, we figure that this patient is severe and deteriorating because we found that his GFR values decreases in the first 32 weeks until the cut point, and his GFR value jumps to about 35. And from the 32nd week, we found that this GFR value remains in a descending trend, means this patient is getting more severe. And furthermore, our model will predict that this, as time further goes on, this descending trend will still go on, and the loss of this patient's GFR values will exceed 5 milliliter per minute per 1.73 square meter within 1 year. So after we consulted the doctors, this means that this patient will need more advance and intervention. So our model would suggest that this patient to consult the specialist for expert assessment. So now let's look at the second patient. This patient is in the mild yet deteriorating progression. Because in the beginning we found that this patient's GFR value only indicates moderately reduced kidney function. However, his GFR value decreases slowly before the 52nd week, and our model predicts that this deterioration will continue and the patient will have a large drop in his GFR value. So our model will suggest healthcare workers to provide more aggressive interventions to this patient. And for the final patient, we find he is severe yet stable. We find that he is already in CKD stage 5, which is already the most severe stage for CKD disease. And our model predicts that this situation will continues together with time. So our model suggests the doctors to guarantee the monitoring for this patient. So to summarize, we identified the irregularity at the feature level in electronic medical records. We figured out that capturing the feature level irregularity can benefit the EMR data analytics. We use the disease progression modeling as an example. We propose our feature level time decay model, and then we evaluate our proposed model using a public ADNI dataset and a private NUH-CKD dataset. That is all. Thank you.